Hi Wayne, hi Travis. This is John Whitaker for the Probability Graduate Level class, and this is our 19th video lecture. And today we're going to talk more about conditional expectation, and we're also going to relate conditional expectation at the end to regular expectation. And we had ended last time talking about conditional expectation for discrete random variables. And today we're going to begin about conditional expectations for continuous random variables. So let's start there. So it's a definition. We'll let x and y be continuous random variables. Then the conditional expectation of x given y is denoted by the expected value of x given y equal to y, and defined by expected value of x given y equal to y is equal to the integral from minus infinity to infinity of x, and here it would be the conditional PDF of x given y, and we integrate with respect to x. So that's the definition of conditional expectation for continuous random variables. Let's look at an example. Let x and y be continuous random variables with joint PDFs f of x comma y equal to, that's an example we looked at before, it's 12x if 0 is less than y is less than 2x is less than 1, and 0 otherwise. And it says find the expected value of x given y equal to y. We had worked with this joint PDF earlier, and what we had found, so we previously found that the conditional PDF of x given y, okay, this was equal to I'll write it a little bit more precise than I did before. It's 8x over 1 plus y squared if 0 is less than 1, is less than 2x, is less than 1, and here it's 0 otherwise. But that's from our previous work. It was in the last video. Okay. So for y being sandwiched in between 0 and 1, and that's the conditions that we have with the conditional probability density function is defined. The expected value of x given y equal to y would be equal to, well, it's an integral, so from minus infinity to infinity is the first thing we say, of x, so x given 1, dx, that's its definition. And then that's the same thing if we look at the region where the conditional PDF is defined. This is 1, 1 half. I have this here. This is y 2x. And it was defined here. Y was less than 2x. And so over this region, for a fixed y, we say for a fixed y, where do the x values run from? They run from this line, y equal to 2x, or x equals to y equal to 1 half. And so that ends up being what I integrate over. So we have y over 2 to 1 half, x, and then what the conditional PDF was, which is not 0, is 8x over 1 plus y squared dx. And you might have thought, well, why don't we just integrate as x runs from 0 to 1 half? Why do we have this bound? It's because this quantity right here is depending upon y, what the fixed y is, or whatever y is. Here, this ends up being 8x cubed. Remember, I'm integrating with respect to y over 3 times 1 minus integrated with respect to x, y squared. I need to evaluate that from y, from x running from y over 2 to x equaling 1 half. When I do, and I stick in 1 half, that ends up being 1 over 3 minus, 3 times 1 minus y squared. And then minus, when I stick in y equal to, x equal to y over 2, the y over 2 cubed is y cubed over 8, so the 8's will cancel, so I have y cubed over 3 times 1 minus y squared. And that ends up being y minus y cubed over 3 times 1 minus y squared. I know that that can be simplified probably, but I'm going to leave it alone. And that's what we get in this example. I said this in the last video and alluded to it just now, but it's this fact, is that the expected value of x given y is a random variable that is a function of the random variable y. So it's not a constant, it's a random variable. And we can extend the definition of the expected value of x given y equal to y by saying we let x and y be random variables. Let g of x be a function of x. the expected value of g of x given y is denoted by the expected value of g of x given y equal to y, and given by the expected value of g of x given y equals to y is equal to, okay, well, I'm going to write it over here because it's got two forms depending upon x and y are discrete. So, the expected value of g of x given y equal to y is defined by, is the sum over all x values of g of x, f of x given y, if x, y are discrete. Here, it's the integral minus infinity to infinity of g of x, f of x given y, dx, if x and y are continuous. Let's look at an example of that. So here, let's let the joint PDF of x and y be, so here it is, f of x comma y is equal to 1/2 y e to the minus x times y if these two things occur. 0 is less than x is less than infinity, and 0 is less than y is less than 2, and 0 otherwise. And so the directions are find the expected value of e raised to the x over 2 given y equal to 1. Okay, so here I'm giving a specific y. Well, our situation is that of dealing with continuous random variables. That's why I have a joint PDF involved. So I'm going to use this second part of the definition, second form of the definition here for the conditional expectation. So note the conditional expectation of ex over 2 given y equal to 1 is equal to, so this will be the integral from minus infinity to infinity, of e to the x over 2 f of x given y of x given 1 dx. So I need to compute this. So now f of x given y x1, x given y equal 1, that's equal to, by definition, f of x comma 1 over f sub y 1. And f of x comma 1, well, that's going to be equal to 1/2 of the right region of y e to the minus, well, I'm sorry, this is the y was 1. So e, it's 1/2 times 1, e to the minus x over f sub y 1. So now I need to find f sub y 1. Well, f sub y of 1, so I'll do it without putting y there directly, I think, that's going to be equal to, so it's the integral from minus infinity to infinity of f of x comma 1 here dx. So let's see, where we're integrating over, where the f of x, y is non-zero, is x runs from 0 to infinity and y runs from 0 to 2. So we're talking about this region right here. That's what we're saying. Okay. And so we know y is equal to 1, and over that region, this integral is the integral from 0 to infinity, okay, which is non-zero, the joint PDF. So this will be 1/2 1/2 y, which is 1, e to the minus x times 1 dx. Okay. Here this is e to the something. To be able to find the antiderivative of e to the something, we need the derivative of the something, which is minus 1. So I'll put the minus 1 there and compensate for it by putting a minus out front. So I get minus 1/2 e to the minus x. I need to evaluate that as x goes from 0 to x equal to infinity. I'm being a little bit informal here. Remember, this should be a proper integral, and I should be taking the limits as t maybe goes to infinity, and x going to t here, or x equal to t here. But I'll do it informally. And say that's equal to, well, when I let x get really, really big, e to really, really big powers, or e to really big negative powers, that goes to 0. So this is like 0 minus a minus 1/2, and then when x is 0, we get out e to the 0, which is 1. So I end up getting 1/2. That's that part right here. So I'll write down on this board that the conditional the conditional density function of x given y equal to 1, it's going to be equal to 1/2 e to the minus x over 1/2, which is just equal to e to the minus x. So, the expected value, what we were looking for, was e to the x over 2, given y equal to 1. We said was the interval from minus infinity to infinity of e to the x over 2 f of x given y x1 dx, which we said, hey, that's the same thing as, okay, so the where this is, we know what this is, we just found it, and where it's non-zero is from 0 to infinity. 0 to infinity, e to the x over 2, here was e to the minus x dx. And so that's equal to the interval from 0 to infinity. When you add these to get a common denominator, you're going to get e to the minus x over 2 dx. And then here again, I need a minus 1/2. I insert that and I have to compensate by putting a minus 2 out front. That's the antiderivative. Let's take in 0 and infinity. Doing this informally. We have huge x values. E to minus huge x values goes to 0. Minus a minus 2. When you let x be equal to 0, you just get e to the 0, which is 1. So you get e to 2. And that's the answer. So the expected value of e to the x over 2 given y equals 1 in this situation is 2. Okay, here's another example. So we let x and y be independent Poisson random variables with parameters lambda sub 1 and lambda sub 2, those are their means. And here's what we're supposed to do. We're supposed to calculate the expected value of x given x plus y equals to some number n. Okay, so here's where we start to solve the problem. Note the expected value of x given x plus y equals 10. By our definition, with us using here discrete random variables, this is going to be equal to the sum over all x values, so they're Poisson, they run from 0 to infinity. Here would be x, that's a conditional probability mass function of x given x plus y of x n. That's what we have. So let's think about what this is. So this is equal to the sum. X runs from 0, well, stop and say no. F sub x plus y, x given n, well, that's equal to f of x n over f sub x plus y n. And in terms of these PMFs, the joint PMF here, this means the probability of x is equal to x, and y, x plus y, that's the other function involved, is equal to n, over the probability that x plus y equals to n. Now, the top can be thought of as the probability that x is equal to x, and for x plus y to be equal to n, where I know that x is equal to x, that means that x plus y, or that y, has to be equal to n minus x. That's the only way. Y would have to be n minus x for x plus y to be equal to n, where we know that x is equal to x, and x is equal to x. So that's what we have there. All over, we had previously worked with having two independent Poisson random variables with parameter lambda 1 and 2. And we said if you add those, then what you get is the addition is a random variable who is a Poisson distributed random variable. Parameters is lambda 1 plus lambda 2. So the probability that this is equal to n, I can write that down. It's e to the minus the parameter, which is lambda 1 plus lambda 2, the parameter, which is lambda 1 plus lambda 2, raised to the n, all over n factorial. Here, we know x and y by our hypothesis are independent. And so, since that's the case, this is the probability that x is equal to x times the probability that y is equal to n minus x over, here, this bottom part I'll just leave the same. So lambda 1 plus lambda 2 to the n all over n factorial. Okay. So that top part becomes, this was e to the minus lambda 1 to x over x factorial times, here this would be e to the minus lambda 2, it would be lambda 2 to the n minus x over n minus x factorial. And then it's all over that quantity, which I'll flip. And this is n factorial over e to the minus quantity lambda 1 plus lambda 2 times lambda 1 plus lambda 2 to the n. And I'll rearrange things. I'll say this is n factorial over n minus x factorial, that's in the bottom. And then I'll say, well, here we have e to the minus lambda 1, e to the minus lambda 2. They're multiplied together. That would be e to the quantity minus lambda 1 plus lambda 2, which would cancel with this guy. Then I'll say we have lambda 1 to the x over, I'll rewrite that bottom as lambda 1 plus lambda 2 to the x times lambda 1 plus lambda 2 the n minus x. So it was raised to the n, but the raised to n minus x, raised to x, you would add the exponents here, so we just get n, so that's that part. And then here's this lambda to 2 raised to n minus x. Well, this is the same thing as n choose x. Here I'll rewrite this as lambda 1 over lambda 1 plus lambda 2 raised to x. And here, this is lambda 2 over lambda 1 plus lambda 2 raised to the n minus x. Now, what I want you to notice here is that if you were to take lambda 1 over lambda 1 plus lambda 2 and add to it lambda 2 over lambda 1 plus lambda 2, you get 1. And so this can be thought of as a number, and it's going to be between 0 and 1, so you think of it as probability in some sense. We'll call it little p. And right here, this is 1 minus that number right here, so 1 minus p. So what this says right here is this looks like the PMF of a binomial random variable. So that's what I'm going to write. So the conditional PMF of x given x plus y for independent Poisson random variables is a binomial random variable. And I'm going to say, so the parameters are p equal to lambda 1 over lambda 1 plus lambda 2 and n. Okay, those are the parameters. Let's don't forget what we're trying to find. So, the expected value of x given x plus y equals 10, which we know to be the sum that's over all x values, they run from 0 to infinity, of x times f of x given y that we just found this part. But one thing I want to tell you, if we know that x plus y is equal to n, the maximum value that x can be, because y can never be 0, is n. So when you get x value bigger than n, that is impossible. So this sum, we get 0 in those cases. This sum would be from x running from 0 to n of x, and in this case, this quantity we know is n choose x, and then it was lambda 1 over lambda 1 plus lambda 2 raised to x, and then here it was lambda 2 over lambda 1 plus lambda 2 raised to the n minus x. Okay, that's what we are. But that is the expected value of a binomial random variable, x, with these parameters, n, lambda 1 over lambda 2, lambda 1 plus lambda 2, and n. So the expected value of that is n times p, so n times lambda 1 over lambda 1 plus lambda 2. That's what we get. And that's the answer. Let me write down the fact, prove it. It says the following. It says we're going to let x and y be continuous random variables with joint PDF f of x comma y, then the PDF of x and, so this should be the joint PDF of x and x plus y is f, and I'll rewrite this as x and x plus y, because I have several things running around. I'm going to say little x and t, which is going to be the same thing as the joint, so this is joint. The joint PDF between x and y of x, and then it's t minus x. Okay. Let me go back here in terms of my notation, and let us write this as x, y in that fashion. Sorry about that. We're going to prove this. So we let x and y be continuous. Random variables. With joint PDF f of x comma y of x. Here I'll write down y that way. Now we're going to let the joint CDF cumulative distribution function be denoted by f of, I'll write down xt. Okay. Which we know to be equal to the probability, well, let me write it on the circle. And I didn't write down anything. Let the joint CDF, let's just call it f of xt. All right. I don't like whatever. Let the joint CDF of x and x plus y be denoted. B f of x comma t. So that is the joint CDF of x and x plus y. And so we can relate that to the joint PDF in just a second through differentiation. Note f of x comma t. What that's equal to, you could put x and x plus y here, because that's what we're talking about. If you want to go back, change this, you can. It's okay. So the notation is very consistent, clear. Okay. Well, what does this mean? This is the probability that x is less than or equal to x, and x plus y is less than or equal to t. And in terms of a picture, if I call this u, which is really representing x, the variable x, and this is v, which really represents the variable y. Okay. So x plus y equal to t. So if this was t and this was t, you'd have this line. That line. And where the x plus y is, and maybe that's x, you have this line. So the x is, we want the region where x is, big X is less than x. That's all over here, but we also want this region. So we're talking about this right here. This is where we'll be integrating. That's the region. So this is equal to double integral from minus infinity to x is what it would be. So that's what the x values would run from. Except I'm not going to call them x, I'm going to call them u values. Here, we have another interval. F of u v. I'm going to write down dv, du, because du are like the x values. Okay? So I've switched from what I standardly do in terms of the order of integration. And here, the v variable, y variables, for a fixed x, they run from minus infinity up to this line. Now here, I'm thinking this is x plus y equals to t, but because I'm rewriting this, this is like u plus v equals t, in terms of the dummy variables, u and v. Okay? And so here, this means that v would run from t minus u up to t minus u. And that's what this line is, t minus u. And here, what we're thinking of is that this is the joint PDF of x with y. Okay? That's what this is. So I could write down x comma y here, or u v if you want. Same thing. Okay, so that's something to keep in mind. Now, we also note that if you take the partials with respect to x and t first of f of x plus y, that's the joint CDF here of xt, when you do that, what you're supposed to get, remember we said this, what you're supposed to get is this is the joint PDF of x with x plus y of xt. That's what I'm supposed to get. So that's one of the things that we're supposed to have involved in the conclusion of the statement. Okay? So that's one of the things. Now, also, if we take a look at these partial derivatives, so this is one way of looking at the partial derivatives of the joint CDF. But another way is to say, well, it's the partial derivative of x, partial derivative of t of this quantity, because that's what this joint CDF is. Okay. And so I'll say, well, we can move this to the inside, and so that's the partial with respect to x, integral from minus infinity to x. Here's the partial with respect to t, minus infinity to t minus u of f, so x given 1 of u comma v, okay? And then this is dv du. And so here, this shouldn't be f of x given y. I made a mistake. This is f of x comma y. X given y, side. F of x comma y. It's the joint PDF of x and y. That's what I should have written, so make that change. All right, so here we use the fundamental theorem of calculus. We're integrating with respect to v. We think of u as a constant here. And so using the fundamental theorem of calculus, this guy, the derivative of the integral, just becomes what we're integrating, evaluating at that upper limit. And so that's equal to the partial with respect to x, here from minus infinity to x. And what I would get would be f of x comma y, and I would have u, and instead of v, I would be writing t minus u, and it would be du. Now when we do this integral, what we get is we replace, by fundamental theorem of calculus, we replace the u with x, so we x t minus x, and that's exactly the result that we wanted. So we have f of x, the joint PDF between x and x plus y, and we have x t is equal to the joint PDF between x and y of x and t minus x. So that ends that proof. Okay. What I'd like to look at now is one fact. I'll prove half of it, and then the other half is very similar. And then we'll look at an example, and that'll be it. So here, is a fact is that the expected value of x is equal to the expected value of the conditional expectation of x given y equals y. So the proof, we'll do in cases. So case 1, x and y are discrete. So, when x and y are discrete, what we'll take a look at is that note the expected value of x given y equal to y. So we had a fact that said the expected value of x given y equal to y, the conditional expectation, is a random variable that's a function of y. So what they're discrete. So this is going to be discrete. So this is the sum over all y values. I'm sorry. Over all y values, whatever, of the expected value of x given y equals to y times f sub y of y, the PMF of y. That's what it is. So this is equal to the sum over all y values. Now, the expected value of x given y, it has a definition, and that's the sum over all x values of x. And here we have f, this is the conditional PMF of x given y, and then half times f sub y. Take the time. Okay, let's replace what the conditional PMF is equal to. This is a double sum. The joint over f sub y of y times f sub y of y. Well, of course, the f sub y of the y's will cancel each other out. And this is the sum over y's, the sum over x's of x, f of x comma y. Now, listen, that is the expected value of x, but I'm going to kind of take my time to show that. I'm going to change the order of summation. And then I'm going to pull out the x, as it is a constant with respect to y. And the first sum here, the latter sum, the inner sum, the sums over the y's of the joint, that just yields the PMF of x. And so that is definitely the expected value of x. And so that's the proof in case 1. For case 2, I'm not going to do that, but just make a comment about it. That's x and y are continuous. And in this case, what we do is we say this is analogous. Part of the proof is analogous to case 1, except, as you can expect, we use integration instead of summation. Sometimes the conditional expectations can be easy to calculate, and I want to show an example of where we can use the fact that we just partially proven defined to solve the problem that would involve conditional expectations. So here is an example. Let's say Sam is either going to read one chapter of his probability book or one chapter of his history book. If the number of misprints in a chapter of the probability book is a Poisson random variable, with mean 2 and the number of misprints and a chapter of the history book is a Poisson random variable. With mean 5. History books are more likely to have mistakes than probability books according to this problem. Okay. Here instead of saying if, say suppose. And, okay. Now, assuming Sam is equally likely to choose either of the books to read. Okay. Find the expected value of the number of misprints he sees. He will encounter. So, listen, it turns out that this is very easy to understand. The number of misprints in the probability of books 2, the number per chapter on average, the number in the history book is 5. So on average, with each of them equally likely to be done, half the time it's going to be 5, half the time it's going to be 2, and so really it's 5 plus 2, which is 7 over 2. That's going to be our answer. The way to look at this, way up at this, is that we could say, for our solution, in terms of our theory, so when things are more difficult, we still use this theory. We're going to let x equal to the amount of misprints Sam encounters. Okay, okay, so we're going to also let y equal to 1 if Sam reads the probability book, and 0 if Sam reads the history book. So this puts me in a position where it's easy to compute. The expected value of x. So that's what we're looking for. So we're conditioning, of course, on which book he chooses. So here, note, this is what I really want to find. Expected value of x. Expected value of the number of misprints. This equals to the expected value of the expected value of x given y. Okay. And so this is equal to the expected value. So the expected value is the sum over all y values, 0 to 1, the expected value of x given y equals to 1. This is one way of writing it. It's, I meant to say, times f sub y of y, the PMF of which book you choose. Okay, so this is the expected value of x given y equal to 0 times f sub y of 0, that's the history book situation, plus the expected value of x given y equals to 1, which times f sub y of 1, which is the probability situation. Okay, look, if they tell you that y is equal to 0, you know you pick the history book. The expected value of that, of the misprint you find, is 2 times 1/2, plus here you know you picked the probability book. I'm sorry, this was 2, this was 5. That's the number of misprints in history. Here, the expected value of the number of misprints you encounter 2 in the chapter, times the chance that you pick the history book, that's 1/2. So again, this is 7/2, and that is the right answer. And that concludes this lecture and that sample. Thank you very much for your time and patience.